Hi, welcome, and thank you for joining our webinar in collaboration with IFPRI and Avika today. And it's titled Decoding Particle Science and Technology into Practical Manufacturing. With me is your speaker, Dr. Willie Hendrickson. Hi, Willie. Can you say hi to everyone?
Hi, everybody. Glad you're
Awesome.
here.
Willie is the founder and CEO of Avika, also the president of International Fine Particle Institute, IFPRI. He has authored and co-authored over 20 technical papers, books, chapters, and is an inventor on 50 issue or apply for U.S. patents. My name is Julie Chenuin, and I am your facilitator. We will have a Q&A session at the end. And Willie, the floor is yours. Would you please share your screen?
All right. Julie, thank you for the introduction, and thank all of you that are online for joining us today. I'm a little surprised. My title is odd: Decoding Particle Science and Technology into Practical Manufacturing. I had a different title and it got changed twice. But what I'm going to talk about is how IFPRI can help get particle science and technology into manufacturing. And hopefully the talk will make sense, and hopefully you'll enjoy it. So let's get started. So the outline that's up on the screen right now, I'm going to start out and give some background information. This is a slightly different talk for me. I'm going to talk about the difference between chemistry and particle science and technology, and I hope you find this interesting. The thoughts are going to kind of drive us to where we're going to go in this talk. Why do we care about particle science and technology? I mean, who cares? But we do. I mean, if you're here, hopefully you do. I'm going to give a historical perspective of a point in time in the 1970s that hopefully is going to give us some ideas about particle science and technology. I'm going to talk a little bit about technology readiness levels. Then I'm going to talk about the genesis of IFPRI, the structure of IFPRI, the technical program at IFPRI, and finally a conclusion. So with that, let's get going and see where this all takes us. So, by training, you might not know this, but I am a chemist by training. And, chemistry is one of these technologies, at least in my mind, that's fairly well understood. And in fact, the important part that's understood about chemistry is that we have the techniques for measuring what we do in chemistry. So we typically, if we know the weight, if we know the temperature, and we know the pressure of something, we can do an awful lot of chemistry. And interestingly enough, I went out and tried to find out when were these techniques really invented. And for a weight, at least what I found on the internet is that scales were used in Egypt in 3100 BC. So that's reasonable to guess or to have. So good technology there. But temperature, think about that, the actual measurement of temperature. So what your temperature reaction is or how things are proceeding. Really it wasn't until the 1700s when Daniel Fahrenheit invented the first alcohol thermometer, and then 5 years later he invented the mercury thermometer. There was some work by Galileo beforehand and some work afterwards by Thomas Seebeck on the thermocouple, and the barometer to measure pressure was invented in 1643 by Torricelli. And when I have those techniques, I mean, this is the ability to really measure chemical reactions and what's proceeding. This knowledge has been around for almost 300 years or over 300 years for most of this stuff. And so chemistry is a technology that they seem to have an understanding of how to run a reaction, how to control a reaction. But now let's compare this to particle science, and particularly let's compare it to just one measurement, particle size measurement. Now, in one sense, once again on the internet, I found that sieves were first described in being used in Egypt. And obviously, if you have a series of sieves, you can do a particle size distribution with it, but it's a tedious method and it doesn't necessarily tell you everything about a particle size and distribution. fast forward almost 6,000 years to the Netherlands, and Van Leeuwenhoek invented the microscope. And now he didn't invent it to measure particles, but he was actually looking at microbes under the microscope. But clearly, with the invention of a microscope, you could start looking at particle size measurements. And I have done enough looking at particles under a microscope that I can get a pretty good idea what the D50 of a particle size distribution with the microscope. It's tedious, it's hard, but there's techniques that have been around, but not applied as much perhaps as you would like. In the 1850s, Stokes, our Stokes settling law person, applied settling phenomena, just inverting the viscosity particle size relationship to actually get a particle size measurement using settling, knowing the viscosity and the densities of the material. You could actually come up with a particle size measurement, but once again, hard to do and not necessarily an easy technique. Interestingly, it wasn't until the 1950s that when Wallace Coulter pioneered the electrozone method for particle size measurement that we really had a method for automatically measuring particle size processes. And about 20 years later, Fraunhofer laser diffraction method, and I'll give a plug here for HORIBA on this. This is the one of the techniques that they use in their particle size measurement was finally commercialized. So think about it. Chemistry had all the measurement techniques that they needed to have by the 1700s, early 1700s. And particle size measurement, even though there were ways to do it, but easy ways of doing it, really didn't come around until the 1950s to the 1970s. In one sense, we're at the beginning of particle science and technology. And I think this is one of the reasons that many times we find the challenges in particle science that you don't necessarily find as much in chemistry or physics. So this kind of leads me to the question is, who cares about particle science? Why is it important? And for those of us that work in the area, one of the things that we know is particle science and particles are ubiquitous. They're everywhere in industrial manufacturing. And I would challenge any of us to come up with a material that doesn't use a particle in its manufacturing process or isn't particulate in nature as the final product. Almost everything that I can think of has a particle in it in one form or another. So it is very important. The other thing that makes particle science important, and I think we all live this, is that small changes in particle-related processes and properties can have an incredible effect on the productivity, the quality, and the profitability. And why is that important? Obviously, you're not going to have a job or a company if you don't have a profitable product. But Reg Davies at one time from DuPont calculated that over 40% of the value added to most chemicals was related to particle processing in one way or the other. And this value could be in having the right size or having the right powder flow or having the right reactivity because of a particle property. So particle science and technology is incredibly important for us, all of us in manufacturing. And we have that need to be knowing what we're doing. But just think about it. We've only had 50 or 60 years of good particle size measurement that's easy to do. We are in the infancy of our field here. I know we don't think of that sometimes, but I really think that's true. So let's get some context for the middle of the 20th century, some historical context. And I have a number of points here. I'm going to go through each one of these. And one of the things I want to start with is the invention of the pelletizing process for taconite ore in the 40s, 50s, and 60s. For those of you that aren't from Minnesota like I am, you might not know what taconite is, but taconite is a low-grade iron ore that there's a lot of it in Minnesota. In the 1880s, iron ore deposits were discovered. High-grade iron ore deposits were discovered in northern Minnesota on a number of deposits in the Mesabi Range, the Vermilion, and the Cuyuna Range. And that ended up allowing America to become one of the premier iron producers in the mid-century of the mid 20th century. So prior to the first or the Second World War and after the Second World War, the United States was producing about 60 to 70% of the iron and steel in the world. Now, one of the reasons that they were able to do that is they had this incredible iron ore deposit in northern Minnesota that they could just take away the top layer, dig it up, put it on a boat, ship it through the Great Lakes to Cleveland or Pittsburgh or Buffalo, where the big iron mills, or excuse me, the blast furnaces were, and produce this iron at an incredible cost, good cost, and high volumes. In the 30s, somebody started looking at the iron ore deposits and realized that the iron ore deposits, as big as they were and as good as they were going to run out by the mid 1960s. And so somebody at the University of Minnesota, and I apologize, I don't remember the name, started looking at this and started saying, well, there's this huge deposit of low-grade iron ore that's only about a third iron as opposed to 100% iron oxide for the good deposits. They thought, well, let's see if we can beneficiate this. Let's see if we can grind it up, a particle processing process. Let's see if we can separate it, either by flotation or magnets, and then let's send it off to the blast furnace and see what we can make. So they actually did that. They ground up this the taconite. They got to 10 to 20 micron particles. They sent it off to a blast furnace someplace, put it in the furnace, and it shut the furnace down, completely shut it down. What happened there? Well, the way a blast furnace works, in order to reduce iron oxide to iron ore, you have to pump CO, carbon monoxide, through the system, and that reduces the iron to make the iron metal. And with the small particles that they had with this new version of iron oxide, you couldn't get any air through it, and so it didn't work. Back to the drawing board they went. They found out if we could pelletize it by a balling process, just kind of tumbling it, you could make 3/8 to a 1/2 inch pellets. They fired them, they sent them to the blast furnace again, and another problem happened. Now, instead of shutting the blast furnace down, this new pellet, this new uniform size pellet, made the blast furnaces run 5 times faster. 5 times faster. What this ended up with is the amount of blast furnace that were needed in the United States to produce the same amount of steel dropped by 80%. And this happened over a span of about 10 or 15 years. If you're old enough, you'll remember how the steel industry in America was dying. It wasn't dying, it was changing because of particle technology. This particle technology, this pelletization process, is done around the world right now. It is one of the reasons that metals, steel, and iron is relatively cheap, because you can operate so much more efficiently. I think this is one of the truly great discoveries in particle science and technology. All happened in that mid 20th century. If we get into the 70s, there were some people that were starting to notice these sorts of things, particularly in some academic schools around the US and Europe and Japan. Bob Pfeffer at City College, Len Austin in Pennsylvania, the Rumpf School in Germany, the Japanese school headed by Anoya, and Brian Scarlett was at Loughborough at the time. And these people were realizing that particle science had a lot to offer, but there seemed to be a whole bunch of disconnects that were going on that were troubling. As I mentioned earlier, in the 70s, the Fraunhofer laser diffraction method was developed, and it kind of opened up a lot of studies going on. Some other things that aren't on here, Derek Geldart in the UK came up with a classification, the Geldart series of powders. Janicki and Johansson came up with some good powder flow measurements. It was almost a golden age in the mid 20th century for particle science and technology. Beyond this, in 1974, Stan Saden at NASA conceived of the technology readiness levels on a way of evaluating technology. Is it ready to go to manufacturing or to be used in space operations? this was a really kind of an interesting departure from, we'll just kind of work at it till we're ready, but to actually define this is going to have a big impact. I'm going to talk about this a little bit in just a second about how we commercialize products. And finally, in 1979, IFPRI was founded to promote particle science and technology from an industrial standpoint. And finally, Ed Merrill published a paper in Chem Engineering, that's CHEM, not N, estimating startup times in solid processing plants. And what he found was starting up a solids processing plant was much harder than starting up a liquids or solid handling processing plant. And for those of us, once again, that are in particle science and technology, we know that. It's incredibly difficult to get a piece of equipment going that at the rates and the volumes and the optimization that you want in a solids plant as opposed to a chemistry plant. So think about this. In the 70s, new technologies were there. People were starting to realize that we need to manage our technologies with the technology readiness levels that I'm going to talk about in just a second. There were people that were thinking about particle science and technology with some proof with the taconite pelleting process was much more important than just a second cousin. There was something that needed to be done, and there's something that needed to be done to make us be able to get products commercialized faster. So those of you that have listened to some of my talks in the past, earlier this year in January, I gave a talk on commercialization and transitioning through the Valley of Death, where I specifically talked about these technology readiness levels. And I suggest or highly suggest that you go and listen to that talk if you're interested in commercialization. I'm going to give just a small subset of it here. One of the things that Stan Sadin came up with in his technology readiness levels that you see on the left side of the screen is the idea that there's different levels as you go through this commercialization process. From you have a good idea to benchtop testing to prototypes to finally commercialization. And if you know where you're at, you know what kind of resources that you need. Graphically, this is shown on the right side of the screen, where you're looking at basic research on the left side of the graph, with the dip, which is the Valley of Death, that technical development, that pilot scale work, to finally commercialization at the right, where you can start actually making money. I talked about this in a general form in the talk in January, but the reality is, in particle processing, not having all the techniques for measuring that we would like to have, or not having all the fundamental understanding that we would like to have, getting through this Valley of Death, scaling up something can be a real challenge. So let's just take a look at this and talk about this as a function of how people differently approach industrial or academia and industrial commercialization approaches. The similarities are, inventors are really good at coming up with a good idea and kind of getting it to a spot where they've made grams or pounds of material. But boy, they're not necessarily very good at trying to get through the Valley of Death, that scale-up process. That's a special talent. And realistically, what you need to get through the Valley of Death, beyond a 20-mule team for hauling borax out of Death Valley, is you need lots of money. And you need time and money to get to that. Academics and industrial people both have the challenge of this Valley of Death. Each of them approach it differently. Academia typically starts, with much more novel concepts based on fundamental research, lots of equations, and their equipment that they're using to do these development is a lot of characterization equipment. Now, this isn't necessarily true all the time, but I think in general, this is the case. Industry, when you're an industrial researcher, scientist, engineer, boy, you're going to look at standard processes. You're going to do some applied research. You're going to need to understand some of the fundamentals, but you're going to be really looking at not equations so much as process optimization numbers. And instead of small equipment, you're going to be looking at large multi-unit op equipment, shown at the two pictures at the bottom. This is a fundamental difference on how industry approaches a problem and academia approaches a problem, and yet we're closely tied together. So, trying to get through the valley of death, why is this commercialization so difficult? Well, when you think about it, where you start when you're doing small scale, you don't really care about how inefficient it is. You just need to make those grams or milligrams of material so you can show that you've got a good idea. You typically, when people are starting out with a process, they really don't even consider alternative processes. And many times you choose the piece of equipment that you have there, and those might be bad choices of equipment. I can say when I talk to inventors, be it they come from academia or industry, that mass balance, no, that's hardly ever done. And realistically, once you're done with that first discovery, you think it's going to be so easy. No one thinks about having enough money to get through that scale-up process. Having said that, you're pushing this rope through the commercialization valley of death as an inventor, and one would hope that the plants, the commercial people, are really going to be there to finally grab a hold of that rope and pull it the rest of the way in. Well, that's not really true either, because when you really think about what's going on in a commercial application, they want to run the same process and equipment with the same trained operators, and you come in with a new product or a process, no one's interested in that. And so there's roadblocks that are put up. So you've almost got through the valley of death. You think you're there, somebody's going to help you, and it doesn't happen. Now, that's a general description. If you really put this into a particle science and technology area where all the tools that we have aren't as good as, let's say, chemistry or physics, it makes it doubly hard. So this is the 1970s. People are starting to think about this. They're thinking about, how can we help people commercialize better? What do we need to do? So in the 70s, the professors that are thinking about this, they've made some observations. They made some observations that really, in particle science and technology, there still is a fundamental lack of particle science understanding. And this is true 50 years later. This is a challenge. There's a lack, there's always been a lack for discussion of particle science and technology. Now, you can go to the AICHE meetings, or you can go to an ACS meeting, and there's people that are giving talks on particle science and technology, more at the AICHE meeting than the ACS. But boy, it's hard to have a good sit-down discussion about, what's really going on. How can I approach this? And finally, the universities and industry, even though many of the people working in industry come from university training background, in fact, that's really the case. Once these people leave, there's not a lot of flow back of what's really important, what's needed. So the academics don't really know how to help out, and the industrial people haven't reached out to ask this. So in the 70s, this idea was, these are some of the challenges that are going on. Can we provide a venue for particle science and technology discussion? And that was one of the real missions for IFPRI when they started. Can you develop a pre-competitive strategic plan for particle science? Now think about this. You'd like to get together to talk about this, but you really can't talk about the secrets that you're doing. So any strategic plan for particle science and technology has to be pre-competitive. It has to be open for all to use, and then you can file your patents or your trade secrets after that. And the third thing is, and this is a change from many of the consortiums that are university located or run, is that the R&D focus needed to really be based on industrial concerns. And so in the 1970s, this was kind of the thoughts, the landscape, the thoughts on how can we do this to help us get commercialization going. So in 1979, Bob Pfeffer and Brian Scarlett came up with this idea, and they approached Howard Turner at DuPont and said, we have this idea, we think we need to get together, we need to get a group together so we can talk about particle science and technology. Can you help us do this? Howard Turner, was a bit of a visionary. And I think, as it was described to me, he was also looking for a new job because he was about to retire, and says, I think this is a great idea. Let's expand it beyond City College in Loughborough. Let's get some other people. And so Pfeffer and Scarlett started talking to Lashansky and Neue and Tiller in Germany, Japan, and Texas, came up with this plan. Howard Turner called some of his friends together, and in 1979 in Wilmington, 12 companies got together that are listed here to talk about how to put together a consortium to help people understand and foster this commercialization of particle science and technology. Now, if you look at this list here, some of these companies don't exist anymore. Exxon doesn't exist as Exxon anymore. It's ExxonMobil. Standard Oil of Indiana doesn't exist anymore. U.S. Steel and Bethlehem Steel are competitors, were competitors at the time, and I'm not sure if they exist anymore, to be honest. DuPont was a direct competitor with ICI. 3M competed with DuPont, Procter & Gamble, and Unilever. I mean, this is an incredible group of big companies that had a lot of interest in particle science and technology. How could they get together and actually talk about this and come up with a consistent plan that everybody would be interested in? And I think that's one of the real interesting and great aspects about IFPRI, is having these companies that are competitors, or they're not even in the same area, but can still work together. And I'm going to describe how this is done as we go forward here. So at that first meeting, the IFPRI members decided that there should be 5 main areas that they're interested in from a research program. Characterization and measurement, let's go back to the Fraunhofer particle size measurement, particle formation, size reduction or grinding, dry powder flow, or just movement of powders, solids handling. And finally, what is listed here is sols and dispersions, which we've called wet systems. In between each of these, there's connections. In between size reduction and powder flow, there's attrition. And in between particle formation and sols, there's things like interparticle forces. These all kind of come together. And this was the original kind of technical program structure that IFPRI put together. The idea is that the members would get together, look at this technical program, and find research projects that they could fund with their membership fees at in academia, that would be non-competitive and be valued to everybody else. Now, over the years, the IFPRI members have determined that engineered products, or products that take more than 1 unit op, that might be a particle formation and a size reduction, should be a separate area of research because it's more complicated. And the members have also identified that kind of line in this whole field, educating the students and educating the employees of the companies was also important. So in this context, in that 1979 meeting, the idea was, let's figure out how we can get this technology out. Let's see how we can use it to commercialize better. And eventually what IFPRI came up with is what we call the IFPRI Deliverables. I would say one of the most important things that IFPRI came up with was what I would call the interpersonal forum, where people get together and in a non-confrontational situation talk about particle science and technology. Originally, they got together once a year at an annual general meeting that I'll describe in just a bit. And this was to talk about the research that was done and to plan new research. They've expanded it over the years to have a second meeting, a winter business meeting, and we have monthly update conference calls. And this is to have that connectivity between people that are doing this very hard research in particle science and technology and trying to apply it to the commercial aspects. Gives us a chance to talk about some of these things without revealing the secrets once again. That's always the challenge. Originally, they had a defined industrial strategy that I just described, and it was basically based on a technical research program that I'm going to describe in just a little bit in those 5 or 6 areas that were there. They also had some technical reviews, but once again, over the years, the members have decided that there's other things that need to be in place in there. things like focused workshops that I'll talk about in just a bit, and roundtable best practices on how to really get down to the nitty gritty and figure out how do we do this the best possible way. There's always been written reports. Early on, there was probably 5 to 6 reports a year. Because the program has grown and IFPRI has grown over the years, we're now producing somewhere between 18 and 20 reports, some reviews, and we have over 700 reports and reviews online for people to look at, to go back and find new information, or kind of harvest that old information to come up with new ideas. Now, the one thing that wasn't in the original plan, other than we're going to pay attention to education, was an education program. And just recently, IFPRI started to look at this, that we need to better educate the current employees that we have, and we need to ask the universities to give us better educated people that we can actually use. And that's one of the things that I'll talk about also. So at an IFPRI meeting, the annual general meeting that we have once a year, it's a 5-day meeting. There's a number of things that goes on at these meetings. To start with, there's reports from our academic grantees. So typically these are short presentations. So we've defined the projects, they've done work for a year. They now are going to give us a short presentation. Then we're going to break up into small groups, and we're going to spend time with each one of these people. It's set up so you can have a small group discussion with a professor and really ask them questions that you might be less inclined to ask in a big group setting. So you can start developing these conversations, and professors like to hear these conversations, because what they're really getting is what industry is really interested in, which helps them kind of plan where they want to go with their work. And finally, because we're paying for this, because we've defined the programs, we've asked them to do research in a specific area, we'd like to give them feedback, and we usually like to tell them that they're doing a great job and keep it up, and we want to fund you next year. But sometimes we tell them, you're not doing a great job, and if you don't change, we won't fund you anymore. So in this particular case, the industrial people, the people that are paying the bills, are really controlling what the research program is and demanding this from the academics. It's interesting, the academics always feel like they're really put on the spot, because the people that are at these IFPRI meetings from the companies are usually very, very well versed in the science and technology. So the hard questions are asked, lots of great discussions go on. That sort of interpersonal forum that I really think is important. These discussions go on long after the poster talks. Goes on. We're eating meals together. We're having happy hours together, and people are spending a lot of time talking about particle science and technology for 5 days. We also have reviews that are presented. We also have invited presentations. But probably the most important part about an IFPRI meeting is, after we've gone through these invited presentations and talked to got an update from the academics on what they've done, we break into small group discussions to talk about new areas of research. And once again, this is driven by the industrial people. What do they think is important? How do they want to do this? And what they end up doing is, in these discussions in these small groups, and then we get back together and talk, and then they go back to small groups, there's some writing of briefs, which are really a proposal that people would like to see research done in a specific area. And finally, at the end of the meeting, we vote on which programs we're going to put forward to ask for new proposals, and which programs are going to be funded going forward. This is really the strength of IFPRI, because here, as a member, you know that you have a problem in an area, that I can't get my spray dryer to operate right. I need a new technology for making a specific type of material. These fundamental research projects can help with that, and it actually gives us the information to help us be better at our commercialization. We also have a poster session. We bring in students from around the area, wherever our meetings are, usually 1 year in Europe and then 1 year in the United States, back and forth. And then that informal discussion that I talked about, we're eating meals together for 5 days. There's happy hours. We have a few sporting events that are not painful to do, and it can be a lot of fun. It develops a lot of camaraderie in the people that are at these meetings, and the conversations just go on and on and on. It's an incredibly exhausting and exuberant type of meeting. So once again, just to remind us, remember, we're taking our money, we're funding research projects in these areas, and every year that the program changes, we fund programs with academics for 3 to 6 years, depending on how much we like it. Less if we really dislike it, we'll cut the projects off. And just to give you an idea, this is the current research programs for this year. I believe there's about 15 or 16 of them on this list here. And I've grouped them by which area that they're in. We don't have one in characterization this year. It ebbs and flows. But right now there's a good number of projects in formation, dry systems, and wet systems. One project in systems engineering and one project in size reduction. Now, once again, these projects change every year. But I want you to note, the things that are here, they're all about how we can do things better, understand better, commercialize faster, to be better at what we're doing. So an example of one of the things, there's a project by Aaron Coos at Leuven, slurry and paste rheology. Rheology is important, how the toothpaste flows out of the tube, or how things move out in an extruder. And over the years, we've gone from low solids rheology systems to high solids, because at the end of the day, that's what a product is. So having Aaron do some research on this slurry and paste rheology really gets us into the fundamentals that we need to have in order to be more, being able to commercialize better. You can look at there's a lot of work in the dry systems. People are very interested in dry powder rheology. This is because at the end of the day, one of the things that we find, and all of us I think find, is that moving powders from one hopper to another, or feeders, or pneumatically conveying, can be one of the hardest things to control and keep under control. And so there's a lot of interest from the members in that. Every year this changes depending on what people are interested in. And let me just give you an example of how that works here. I'm going to jump ahead one slide. These are the research proposals that the members put together, called the project briefs for 2022. There were 5 of them, 5 proposals that people came together with, that the number of members could get together and agree that we need to understand spray droplet formation. We need to understand drying of paste, spray drying of paste. We need to understand aeration and de-aeration of Gildert Group C particles during flow. Typically, we ask that 2 researchers are given the brief, and we specifically ask people to give us a proposal based on our briefs. You note here that this year, for some reason, we were only able to get 1 proposal for computational modeling of suspensions, Rosanna Zia at Stanford. But we did get 2 proposals from Heather Amati at ASU, and I believe it's Alan Surratt at UC Santa Barbara. The idea is that in our next upcoming meeting, we will take these proposals, people will discuss them, and they will vote on what they want to fund for new projects going next year. I'm going to go back a slide here. Not only do we have the research projects, but this year we have 2 reviews, one on dynamic powder flow that Nico Gray is going to be presenting to us at the meeting, and one on horizons and granular modeling beyond DEM by Franhak Rajai at University of Montpellier. We also have some collaboration projects where we think that we've got really good projects going on, but we need more help with it. It turns out, interestingly, both collaborators come from North Carolina State University. One's working with Prabhunath in India, and the other's working with Jan Vermont and ETH Zurich. We also have a program where we wanted to look at how good are we at DEM simulations, and we all think that we're really good at it. But let's actually compare and contrast. So we asked Jonathan Seville at University of Birmingham to run a program where he would set up easy to model powder flow measurement systems, analyze them, and then ask IFPRI members to do DEM simulations and compare and contrast to see what is the best practice in here. This is an example where we can do something that isn't proprietary, but together the members can work to find out what's the best way to come up with a good solution for DEM. And finally, we have set up a workshop for this year, but I don't think it's going to happen. And I will talk about workshops in just a second and what they are. And then the last thing on this slide is, remember I mentioned Ed Merrow's report that he did in 1988. He also, there was a pre-report in 85 and a pre-report in the 70s, where he was looking at the difficulty of doing powder flow and solids scale up and commercialization of new plants with solids handling. Well, this is a paper that we commonly in our field reference to talk about the difficulties of particle processing. But this article is 34 years old at best, and so we've actually authorized some money to pay Ed Merrow to do another report on this area, and hopefully he will do this with his company IPA. We're really looking forward to this because this is going to help us show our management, the difficulties of this and why we need to invest more in particle science and technology. Now, the membership in IFPRI over the years has waxed and waned. It's currently at 38 members. These are the full members. These are the members that vote on the projects. I'm going to talk about associate members in just a second. And once again, you can see that there's the same sort of issue that started out with the 12 members. AbbVie, Vertex Pharmaceuticals, Pfizer, Merck, these are all, Hoffman La Roche, these are all companies that compete against each other, but yet together they can actually come together and help us develop a good research program and get value from this. The other thing is that when you look at it, a company like Chemours or Unilever are not necessarily pharmaceutical companies, but yet the fact that we have all these different industrial people there with their different points of view give us a very broad view of the science and technology, and the conversations that go on and the discussions and how we come up with the right proposals and why it's important, I think has a lot of strength because of the breadth and variety of the number of companies, different types of companies that are here. As I said, there are also associate members. These are typically smaller companies. They don't have voting rights. They pay a lower fee to join. And typically they're companies that are equipment manufacturers, software companies, or just plain small companies. Sila Nanotechnologies is a small battery company, but a company like BPEX or Schenck, which are equipment provider companies. HORIBA, which is a member, and thank you, Julie, for having this part of your IFPRI membership sponsoring these sorts of talks. Is obviously a particle size measurement company. Total 38 members currently. Will probably have 2 or 3 more members join us for our June meeting. And you can see, the pharma, the chemical, the ceramics, the agriculture, the modeling, just a wide variety of companies. And once again, I think this really gives that breadth and broadness of our understanding of the technology. Being able to talk to these people will always give you new thoughts and directions to think about. We don't have to talk about proprietary things, and we specifically do not talk about that, but just understanding why somebody thinks it's important to do powder flow measurements means that I should be thinking about that. Maybe it'll help me do my processing better, and it does. So let's kind of wind up here. I've got another 4 or 5 slides, maybe a few more, to talk about some of the other aspects of IFPRI. This is kind of like a Ronco commercial, and there's yet more to be seen here. We have the research projects, we have the reviews, but we also have workshops. And I said that workshops are a great model for us to use for strategic development. Typically, we do one of these once a year or once every other year. They're a 2-day format. We start out with 2 to 3 core questions on a particular topic. We have some presentations. We have a number of people that attend, 30 to 60 people, and these are from around the world. Not all IFPRI members, not all industrial, kind of a mix of IFPRI, academic, industrial. And what we do is we pose these questions, we break out into breakout discussions, followed by we develop an action plan, we recommend some programs. So this helps us come up with new research projects for the next year going forward, and we write an internal report. These are incredibly interesting because it's important for us, all these good people, the academics and the industrial people, to get together and really give your opinions about what's going on and why this is important. And at the end of the day, we come up with some pretty good strategic plans based on all this. Over the years, in the past 15 years, we've done about 10 workshops, and you can see that quite a wide variety, from gels to grinding to crystallization to education in particle science and technology to cohesion. Lots of outcomes from this. You know, some of them have been IFPRI projects. Some of them have been sponsored collaboration with the National Science Foundation. The last one, the cohesion workshop, was right before COVID started, and we lost a little momentum with that project. And hopefully this year, when we finally get back together again after 2 years, we can reboot this and come up with some new interesting understandings in cohesion. I mentioned earlier we have some roundtable discussions. These are usually short discussions, 2 to 5 hour format, typically teleconference or informal meeting. Lots of industrial best practices. This allows anybody in the organization, you don't have to vote on this. You can say, you know, I'd really like to have a roundtable discussion on why spray dryers don't work. We haven't had one on that, but you could have one on that. And I will help set it up, and we arrange these things. It doesn't cost anything, so we can have as many of these as we want. We've had as few as 5 attendees to these things, and we've had as many as 80 attendees to these things. We don't have academics at these. These are just industrial participants. We could have academics. We just hasn't happened. And we do invite non-member participants in this, just because we want to hear, you know, new ideas outside of what we have. Over the years, you know, we started this in 2015. We've had 5 of these. The latest one is education. I'll talk about that a little bit more. But the first one started out with powder flow measurements in 2015. It was really quite interesting. One of our members that does a lot of powder flow measurement was Tim Bell from DuPont, was interested in, you know, how much of powder flow measurements being used, and what devices, you know, who conducts the test, you know, what is this, you know, what can we do better on this? And it was interesting to have all the members, you know, bring, you know, 1 or 2 slides, you know, talk about what they did. And once again, they're not talking about the actual measurements, but they're talking about why, and the understanding of the philosophy behind this was really an interesting discussion that came out of this. A couple projects actually came out of this because of that. Tim's interest in this, and the members kind of like, yeah, this is interesting. We need to talk more about this. The last roundtable we had was in October, where we talked about education. You know, how can we do better in education? There were 50 attendees that showed up to this 2-hour session. You know, do we need to train the operators better? Do we need to train the engineers better? And in fact, we came up with, we need to do both, and we need to have a little bit better way of doing this. So rather than you know, let people kind of struggle a little bit, let's see if we come up with some education courses that can be commonly used over all the companies. And we formed a subgroup, and we're going to actually talk about putting together a video library, and we're going to continue this discussion at our upcoming AGM. I think this is a very, very important area. Finally, I'm getting close here, so, you know, thank you for continuing to listen. You know, we have that round robin evaluation of DEM modeling that's continuing to go on with the University of Birmingham. We're kind of interested in seeing, can we take this to the next personal idea? You know, we're looking at that Marrow report as an outreach for, you know, really kind of defining what particle science and technology is, and the importance and difficulty of doing it. And we do collaborate with other groups and conferences. There's a Gordon Conference on Granular Flow in Massachusetts this June, July. We're going to have some members there. We're actually co-sponsoring this program. I will be giving a plenary lecture at the World Congress on Particle Technology on how you do commercial particle science and technology. We'll be at the Classification and Comminution Conference in Toulouse, and we're always at the AICHE and the Particle Technology Forum. So in conclusion, IFPRI is an interesting group, world-class associates, world-class authorities, getting together in a format that allows discussion of non-proprietary pre-competitive research. We develop a research plan. If you're going to be an IFPRI member or participate in IFPRI, this is an active participation. You can't not show up to meetings, and you can't not contribute, because you just won't get the value, and nor will the other members get the value of your presence. I believe that along with the technology readiness levels and getting through the valley of death, that definition of that valley of death, IFPRI provides a lot of the tricks and tools to help bridge this valley of death. This is how IFPRI helps people go from particle science and technology to commercialized products. I'd like to end with inviting all of you to attend the next annual general meeting that will be held in Brussels, Belgium, June 12th to the 16th. I will be sending out invites to all of you, and I hope that you can attend, and I appreciate you listening. Thank you very much.
And thank you, Willie, for the excellent talk. I was listening in the background. It sounds like a fun party. Of a lot of great kind of minds coming together and collaborating. So
It really is. It's a lot of excitement at the meetings. We do have some happy hours. We do have lots of fun discussions, but boy, there's a real focus on getting better at what we all do and love.
absolutely. So that being said, a question that came in was, how can I apply for the scholarship being sponsored by IFPRI? Is it available?
A scholarship, was this from an academic, do we know?
Yes. So she
So,
has a,
so, so
go ahead.
the way that IFPRI works is we only send out the proposals to people that we want to write a proposal back to us. So if that person would like to be considered, have them please contact me so I can understand what their area of expertise is, and we can put their name forward.
Absolutely. We also have some comments that came in that said, hey, phenomenal review and perspective. Thoroughly enjoyed it. And then a question that came in, well, this is a comment too. This person has worked with Avica. It's a great company. Just want to put it out there and do a quick shout out for you. Question, what is the most common bottleneck for scale up?
That's a great question. And if I was going to give one answer, I would probably say powder handling, powder flow, whether it's pneumatic flow, emptying a bin, uh, sticking on the walls of your equipment, emptying out a bag and dust all over the place. That is probably the universal biggest problem. And if everybody remembers, it's one of the big areas that IFPRI members want to look at. How can we make powder flow better? How can we understand it better? And that's the one that just can be an incredible bugaboo. I'll give an example. We put in a new dryer, and it was almost exactly the same as the one that it was replacing. We made one small change and paid the price of 6 months worth of work to get that process to have the powder flow the same way with one small change. It was an incredible. One would have never thought that happened, but if
Wow.
you read the Merrill report, you should probably not be surprised. But it was it was kind of a shocker actually at the end of the day.
Well, you're right. I think a few comments in pre-registration that have indicated, hey, I want to upgrade my knowledge on powder technology. People are looking to you, I think, for to share more about particle technology. So we probably ought to do one just on powder.
That would be one. That would be a definite good one to talk about. I mean, it's a huge challenge for everybody.
Absolutely. If you want to know more about method development or powder flow or whatnot, there's really good contents on our website. Okay, I think that's about it. You can also email us at labinfo@horiba.com for any questions and feedback that you may have. The next webinar that we'll be giving is going to be on May 24th, and it will be on jet milling and on ceramics applications. So the title is to be determined, but don't miss it. I want to thank you on behalf of our particle group. Thank you, Willie, IFPRI, and Avika. Thank you so much for attending. We'll see you at our next webinar.
Thank you.
Thank you, everyone. See you next time.